All right, so we are continuing our journey in this unit of trigonometric functions to 6.5 graphs of reciprocal trigonometric functions. And before we go into the graphs of those, we're going to refresh our memory about just graphs of reciprocal functions in general. So if you remember, in last unit, we had our good old friend y equals x squared minus 4. You don't have to draw this, but just to refresh your memory. And we knew that that function had a y-intercept at -4, zeros at -2 and 2. And based on that graph, remember the initial strategy was, could you draw the reciprocal based on knowledge of the original? And weren't there certain characteristics of original that corresponded to key features of reciprocal? What was the main thing? That if this is y equals x squared minus 4, and I want you to graph y equals 1 over x squared minus 4, what would be one of the key things to be able to graph that you would need to use? Zeros become vertical asymptotes, right? Because something that causes a 0 here, now the 0 would be in the denominator, that would be a problem, right? So zeros become vertical asymptotes, right? And horizontal asymptote showed up. You don't have to worry too much about the horizontal asymptote aspect for trig. Okay, that doesn't really come into play. But what else? So I'm gonna start writing some of those rules. So I'm gonna write that one. So I'm gonna say zeros of original function correspond to vertical asymptotes of reciprocal. Yep.
Where it was positive before, it's still positive, and where it was negative, it's still negative.
Good. Positive stayed positive, negative stayed negative. Okay? Positive values. Positive values stay positive values. Is everyone okay that anything before the arrow is original, everything after the arrow is going to be the reciprocal? Yeah? Y values, so the positive values stayed positive and the negative values stayed negative. Yeah? So where the intervals on which the function is positive stay positive, and in intervals where it's negative, they stay negative. But then there was one key feature that switched. Remember what that one was? That was a key feature that switched from original to reciprocal. The increasing and decreasing, right? Increasing interval. Became a decreasing interval. You'll put S's. And then decreasing interval becomes increasing intervals. And putting those pieces of information together, those last four, if you remember, that caused our graph to look something like this, right? Positive and decreasing turned into positive and increasing. Negative and decreasing becomes negative and increasing. Negative and increasing becomes negative and decreasing. And then positive and increasing became positive and decreasing. So what I've just drawn in green there shouldn't be too much of a shock. That was the relationship between the original and the reciprocal. So it turns out the same rules are going to apply to reciprocal trig functions. Okay? So before we go there, let's just maybe to get a little bit of a sneak preview. They're going to agree that's one cycle of y equals sine x. Right? And would you agree that it has zeros at what locations for one cycle of sine? Has zeros at 0, pi, and 2 pi. So let's think about the rules. What's the rule saying? That anywhere there's zeros for this graph of y equals sine x, what's going to show up?
Asymptotes.
Vertical asymptotes. Agreed. So vertical asymptotes will show up here, here, here. Okay? Do you agree that now we have a piece of your graph that's above the x-axis and a piece that's below, separated by asymptotes? The piece that's above is the reciprocal going to stay above?
Yes.
So it's going to stay positive, but would you describe this as being increasing then decreasing? What do you think our function has to do to fit the rules? It has to go?
Decreasing and increasing.
You got it. Oh. So what's in green here, and then over here, do you guys see it's the opposite? It's going to stay negative, but instead of being decreasing and increasing, it's going to go increasing and then decreasing. If I remove the blue, you guys see that this, I'll put the axis back. This is what cosecant x is going to look like. But now we're going to be a little bit formal about it. But just so you guys get the idea of the relationship, I wanted to show you that before we actually get to the nitty gritty of graphing it with a little more preciseness. Okay? All right, so let's give it a whirl. So the first thing we're going to do is we're going to fill in this chart. It's going to be a bit tedious because we're going to fill in this chart, and then for each function we're going to refill it in, but we're going to have it first here. Do you guys get that every value in this chart comes from the unit circle? You have to do some adjustments because we're used to the unit circle just giving us sine and cosine by looking at coordinates, and tan we find by doing y over x, y coordinate over x coordinate. But if you know all values of sine x and cosine x, you also know all values of cosecant x and secant x. They're just the reciprocals, right? They're reciprocals. So you don't have to redraw this. If you have your unit circle, you can redraw it for yourself, or if you want to just bring it to your attention here. I'm just going to put the key values on the axes. And I'm just going to refresh your memory here. Here's root 2 over 2, root 2 over 2. This should be all locked in. Root 3 over 2 half. And right here should be my half root 3 over 2. Again, if I know this, I know everything, right? Everything's just a mirror image of this. So if I want to find values of cosecant x, I'm going to look for all the sine values. Again, sine values are which coordinate here, guys? Sine values are the y values. Do we have a whole bunch of y values right here? And again, if you have the whole circle, you have them all. But all you need to do, if you want to fill in this chart, though, is we don't want to just copy the y values. You want to take the reciprocal at every y value. What's the reciprocal of 0?
Undefined.
Undefined. What's the reciprocal of a half?
2.
What's the reciprocal of root 2 over 2? 2 over root 2, but remember, that's really just root 2. Right? Because root 2 over 2 was rationalized. It's the rationalized version of 1 over root 2 if you take the reciprocal of root 2. Reciprocal of root 3 over 2.
2 root 3 over 3.
Very good. And then reciprocal of 1, 1. And then if you kept going and you did the mirror images over here in quadrant 2, all these same y values. And because we're in quadrant 2, do we go positive, or we stay positive, or do we go to negative for y values? The y values are still positive, but what comes up must go down, and so it's going to be these same values just going down. So it's like we staircase up, now we got to staircase back down. Does that make sense? So the next thing I write is 2 root 3 over 3, root 2, 2, and now I'm over here, reciprocal of 0, undefined. So I now have half a circle to go, but what do you notice about these two quadrants for sine? Negative. But again, do we agree that it's basically going to be the same values we just caught, right, that it's all going to be negative? Because it goes reciprocal of negative half, negative 2, reciprocal of negative root 3 over root 2 over 2, negative root 2. It's just all the same numbers. So negative 2, negative root 2, negative 2 root 3 over 3, negative 1. And then what goes down must come back up. So it's, again, the same numbers, just reversed. Negative 2 root 3 over 3, negative root 2, negative 2, and we end with an undefined. Everyone okay so far? Okay, again, the goal is I should not have to touch my calculator to do this. Okay?
Is that a negative root 2 or just regular?
This is the negative, sorry. My negative kind of stuck on there. Okay? For secant x, We're going to traverse the unit circle again, but instead of looking at the y coordinates, I look at the x coordinates and take reciprocals. So what's the big difference? When I look at the x coordinate of the first point, when the angle is 0, I'm looking at the 1. Reciprocal of 1 is 1. Reciprocal of root 3 over 2, 2 root 3 over 3. Reciprocal of root 2 over 2, root 2. Reciprocal of half 2. Reciprocal of 0, undefined. Okay, now I'm in quadrant 2, but now I'm looking at x coordinates. What do I know happens for x coordinates in quadrant 2? They're now negative. But again, it's mirror image of this. So the mirror image will be negative half, so negative 2, negative root 2, negative 2 root 3 over 3. And then I'm at the x coordinate over here, reciprocal of negative 1, negative 1. And now the x's have gone as negative as you can go, and now they have to come back to the positive. So it's going to be a complete mirror image of this over here. So it'll be negative 2 root 3 over 3, negative root 2, negative 2 undefined, 2 root 2, 2 root 3 over 3, 1. Okay. So what's left? Cotan x. So for cotan x, now you can either find all the tan x values and take reciprocals, or if tan x is y over x, or sine over cos, what's cotan x going to be? Cos over sine, okay, y over x. So I can go y over x, or sorry, x over, I meant x over y, x over y. So cos over sine will be x over y. So 1 over 0, you see what I mean? You're just going to, again, just go the other order. So 1 over 0, undefined. Root 3 over 2 over half. Remember, you can ignore the 2's. Root 3. Root 2 over 2 over root 2 over 2, or just think of root 2 over root 2 is 1. 1 over 2 over root 3 over 2 will be 1 over root 3 or root 3 over 3. 0 over 1, 0. And now it's going to be all of these again, all these repeated, but now we're in quadrant 2, and in quadrant 2, tangent is negative. So cotangent is also negative. So it'll be, again, these values, but just negative, negative, negative. So negative root 3 over 3, negative 1, negative root 3. And I'm now back over here at here, and I go x over y, and I get negative 1 over 0 or undefined again. If I'm into quadrant 3, what do I know about tangent in quadrant 3? Positive. Quadrant 4. Negative. So is it going to be basically copy paste what we just did in the first half? It's going to be the same. So it'll be root 3 1, root 3 over 3 0, negative root 3 over 3, negative 1, negative root 3 undefined. So those are all the numbers. Again, you should be able to do this without touching your calculator. Okay? Now, based on this, we're now going to see what the sketches of these look like. So, I know it seems a bit tedious, but just so you have the reference for the values we're going to plot, we're going to redo each row above each graph. So, you have these on the previous page, so I'm just going to copy it quickly. So undefined 2 root 2, I believe, yeah, 2 root 2, 2 root 3 over 3, and 1, and then 2 root 3 over 3, root 2, 2 undefined, and then I repeat that, just all negative. So it's going to be negative 2, negative root 2, negative 2 root 3 over 3, negative 1, negative 2 root 3 over 3, negative root 2, negative 2 undefined. Okay. So, I set up the graph a little differently. Instead of two cycles starting at 0 and going positive, we're going to go negative and positive here. Here's the good news. We're going to keep the same scale for the horizontal that we have all along. I want 12 squares to equal 2 pi. So 12 squares equals 2 pi, 3 squares equals pi over 2. 6 squares, pi. 9 squares, 3 pi over 2. 12 squares, 2 pi. And if I go in the negatives, it'll be negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi. Okay. So again, because we're dealing with reciprocal functions, and because sine, cosine, and tangent all have zeros, I know that cosecant, secant, and cotangent will all have vertical asymptotes. That's the rule for reciprocal. Zeros become vertical asymptotes. Where am I looking in the chart to indicate my locations of vertical asymptotes? X marks the spot. So where are my vertical asymptotes at? 0, pi, 2 pi. And to extend in the negatives, where would they also exist, guys? At
Negative pi, negative 2 pi.
bingo. Okay. Okay. So remember when we graphed the sinusoidal functions, I said, don't worry so much about the root 2's, right? Like we can pretty much get the shape without worrying about the grayed out parts. We like to keep them around, especially when tangent or cotangent come up, because they're a little nicer for those. But for these ones, they're almost like a little bit too much info. TMI, right? Too much information. So you can still use them, but they're not as required. But every value that's not shaded, we're going to deal with. Now, let's refresh our memory of what these two numbers really are. Because on a graph, I don't just know off the top of my head what root 2 is or what 2 root 3 over 3 is. So let's come up with an approximation for that just for our visual purposes. So root 2 is 1.414. And 2 root 3 over 3 is 1.155. So again, the root 2's we're not going to focus all that much on, but the 2 root 3 over 3's we do need to kind of focus on because they're points that will allow us to get the right shape, right? The more points, the better the shape. So let's start with our first interval from 0 to pi. So let's start, I think it's actually easiest to start right in the middle. What do we know is happening right in between the two asymptotes at pi over 2? I have y value 1. So, I should probably have a scale here. So, is everyone okay if we go like this? 1, 2, negative 1, negative 2. So now that I have that scale, I can now plot this point at pi over 2, 1. Okay, so let's go back to the pi over 6. So does this one seem reasonable enough to graph? Pi over 6, 2. So 1 square over, remember if every 12 squares is 2 pi, and every 3 squares is pi over 2, every 1 square is pi over 6. So pi over 6, 2. And there's also at 5 pi over 6, we're at 1 square away from pi, I'm also at 2. If I only graph those 3 points, the tendency is to turn it into a V shape, and it's not a V shape. So this is why the pi over 3 values are important. So those root 2 root 3 over 3's are 1.155s. Are those pretty close to 1? 1.155. Slightly above, right? So 1 squared to the left and right of 1, I'm 1.15 up, so just barely a little bit up, right? Like 0.1 up, so really close, okay? You still see a little bit of white space, right? But because it is a scale where 0.5 up would be 1.5 would be one full grid square. Every full grid square is 0.5. So 0.1 should be 20% of the square, right? So it should be less than a quarter, just if you kind of get, it's close, just above 1. Now that I plotted those, and I have those 5 points, do I have the idea that I'm going to have, like, again, a U shape? But because of the asymptotes, after I pass through those 2's, I have to head towards the asymptote. If I wanted to, I could also put the 1.414's in. That would be, remember, 1.5 squares to the right and left. But do you guys get it's a little bit of overkill? Like, okay, do I need this point too? Maybe not, right? Like I think my curve was going to go there anyway, if that makes sense. So I don't really need those 1.414's, but feel free to do them if you think it'll help you. And then we join, and then approach asymptote, join, and approach asymptote. And you've got half of 1 cycle. Because now we have to repeat that whole process, except instead of opening upwards, it's going to open downwards. But you guys get it's the same shape, just work down instead of up, right? So right in the middle, 1 down. Again, it's kind of like sine. Once you get used to the pattern, you don't even need to look at the table anymore, right? So I know that in the middle, I'm 1 down, and then 1 square to the right and the left, I'm 1 and a little bit down, 1 and a little bit down, so really close to 1, but just slightly below. And then I know I'm 2 squares away, I'm 2 down. So it's not that bad to get those 5 points. And again, you curve, approach asymptote, curve, and approach asymptote. Again, try your best to go right through the center of those points. Okay? To finish this off, can I complete the pattern going to the left? What would come next going left? An opening down or an opening up here? Follow the pattern. This should be an open down, right? Down is all it's going to alternate. Down, up, down, up, down, up. So this is a down. So again, you shouldn't need to look at any table or like, oh my gosh, what's happening at negative pi over 2? Like you shouldn't need to calculate or you go, okay, it's right in the middle of 2 asymptotes. Right in the middle is 1 down. To the right and left, 1 square is 1.15, so just slightly down, slightly less than 1, and then down -2, down -2, and here comes my shape. Approach asymptote, approach asymptote. Duh. Yep. And then the final one is going to be 1 unit up in the middle, 1 and a little bit up, 1 and a little bit up, 2 up, 2 up, and then open up, approach asymptote, open up, approach asymptote. So once you get the hang of it, it's not that bad to draw. Does that make sense? So that's the shape that we're working for this graph. So this is the graph of cosecant. Do you agree that probably this isn't going to be like modeling a whole bunch of real life situations, right? It's not the most, useful graph potentially, but it does exist, so we have to at least deal with it.
Yeah, that would be, what would it even model? Like,
it wouldn't, like, for multiple values it wouldn't, but maybe like a little chunk works for a certain case, and maybe like on a certain interval this graph would work, but it's more, I don't really know any applications of it, to be honest with you. In my math, when I did math at university, I don't think I ever came across a real life situation that could be modeled with cosecant. But if you're not really worrying about the real life context and just about working with a function and being able to do things with the function, then you still need to know how to deal with this function. So there it is. Now we're going to state some characteristics. And for the characteristics, again, I kind of want to do it like with tan x. Instead of starting with domain, let's start with the last thing in this list here, the general form for the equation of the vertical asymptote. So k comes back, right? We want to write things in general. So if you had to describe where all the vertical asymptotes are as an expression, what would you say? The general form of the vertical asymptote, every vertical asymptote is of the form x equals
k pi.
K pi, where k is an integer. Is it even odd pies, even pies, want all the pies, right? Want our hands in lots of pies. No? Okay, x equals k pi, where k must be an integer. Period 1 was all obsessed with this, looks like Legend of Zelda, but anyway. It just means integers, fancy integers. That's what this is. Okay? So, if that's where every vertical asymptote exists, then what's your domain going to be? If those are all the places where the asymptotes exist, then in order to say the domain, which is where the green graph exists, you're going to say
Everything but.
everywhere but that. So this just basically turns into a not equal, but everything else is, x can be everything except those. So x element reals such that x is not allowed to be k pi, where k is an integer. Okay, what do you think about the range here? What y values are possible? Is it y element reals? Can y be everything?
No.
Well, what do you notice about this? There's like,
From -1 to 1.
is blank. So -1 to 1 is don't want. So how do I, instead of saying what don't I want, what do I want? What's left?
Everything.
From
Infinity.
from negative infinity to -1, jump, and then from 1 to infinity. Yeah. So y is negative infinity to -1. Do I get to include -1?
Yes.
It's in my table, so it's fine. And then from 1 to infinity. Do you want to keep with set notation? Y element real such that y less than or equal to -1, comma, y greater than or equal to 1. Okay, here, what?
Can we use mix?
I'm fine. I'm fine with that. You can mix it up. Okay, so period. How long is one cycle? How often does this repeat? Even though you might go, oh, the little u, like, but it's an upwards u and a downwards u together is a cycle. So it's still 2 pi. It's got to match its reciprocal. If its reciprocal sign has a period of 2 pi, its reciprocal will have the same period. So 2 pi. Okay. Location of local max values in general. So let's take a step back here. So I will not ask you for these on the test, but I just want you to kind of start thinking about this because they do come up in the next course. A local maximum means that it's not the maximum of the whole function, but in a small neighborhood, it's the maximum. So can you kind of see that because the function goes off to infinity and down to negative infinity, there's no actual max or min value to this function. But locally, the way this shape looks, are there locations that locally are maxes and mins?
Yeah.
So let's see if we can identify one. Can you tell me from this graph, you have 2 options, a location of a local maximum. Location means tell me the x value.
Oh.
Location of a max, local max. So nearby, all the values nearby are lower than this at this location. Yep,
Can you see 3 pi over 2?
agreed. Does everyone see that in a local neighborhood here, this point is the highest in this little neighborhood? That's your definition of a local max. Like in a small neighborhood around x, it's the biggest, it's the highest location. Okay? So we know 3 pi over 2 is one location. How often do you think local maxes are going to appear? Every 2 pi. So we know how to do that generally. We want to keep adding 2 pi's to k pi, right? 2k pi. So we're going to say 3 pi over 2 plus 2k pi, where k is an integer. And again, if you wanted to write that in a single expression and factor out the pi, we showed you that with when we did it with in the sine, cos, tan lesson. But I'm totally fine with that. That's correct. So I would take that on the test. That's fine. I think it's just easier to even read because it's like, oh, it's there, and then every 2 pi there's another one. I can go positive or negative, but every 2 pi there'll be a local max. Yes.
You don't have to like transform it all.
You will never have to do transformations with cotan x, secant x, cosecant x, or tan x. No transformations. But I'm telling you right now on the test, communication, there's going to be like either a chart or fill in the blanks. And it could be, for cosecant x, state the location of the vertical asymptotes. For secant x, tell me what the period is. For tan x, tell me where the zeros are generally. Like, you know what I mean? Like, you have to know for the parent all those key locations.
So you just memorize those?
You just memorize those, and yeah, you basically have to memorize those, and hopefully this sheet will kind of help you solidify that for yourselves. Okay. Let's move along. Location of local min, so very similar argument. So I pick a local min value, and so where do you notice there being a local min? There's two options again. You could pick any either one. Pi over 2, and then again, how often will a local min happen? Every, yeah.
Good afternoon, residents. Please pay attention to the following announcement. Attention all levels. If you are interested in one, three, and under six, come join the Order of Reciprocal. There will be a brief information meeting in the library after school on Tuesday, November 13th. All are welcome. Please be there. Continuing this week from November, the library will be open during period 3A.
On Friday, the circle quiz, filling in unit circle.
The library closes 2 minutes after school, Wednesday, November 14th. Tomorrow, Tuesday, November 6th, Literacy Tuesday, will all take text. This week's Literacy Tuesday will take place period 2 and cover lessons.
Okay, while we're waiting, I'm gonna put this number in there.
Lots to do and don't know where to begin. Learn how to manage your time and get things done. Join us for a study skills seminar, productivity hacks on Wednesday, November 14th, after school in 332. See Michael Redan and Nick.
You don't even have to move, guys. You can just stay here for that workshop.
Is that here?
Yeah. It's on
There will
Wednesday.
be a sexuality and gender acceptance club meeting today after school in 321 and 8. All are welcome to attend.
Did we do the minimum
Peer
one?
ministry. Please join us.
Uh-huh.
Please join us for peer ministry this Wednesday,
The other
November
chart?
14th. After
Yeah, we did the
Yeah.
minimum.
it's
It's pi over 2. Sorry, yeah.
we have a discussion about very controversial topics. All are most welcome. And now for your general athletics. Hey, Redmond. Hey, everyone. Here are American Board of students for their outstanding commitment, hard work, and dedication to the work we offer. This week, we are recognizing a student athlete who participated in this year's World Season. This student plays third in the state of this week, actually including Cole Becky as a captain of the team. Congratulations, Billy. And now for a short announcement about intermural.
Dear Reverend, Bill, grateful. Just as great as that for the preview launch from this week on. Next Thursday, we have a great night planned for the volleyball and for those who have to sign up, please keep applicant costs with your gym clothes, your running shoes, very important, and have some water because you're going to sweat. So just a reminder, so today, we actually go to set starting tomorrow. Thank you.
That's all for the end of the day announcements, and I hope you have a great rest of your day.
Okay, guys. So there's your setup for, again, nothing's changed. It's the exact same setup we had for y equals cosecant x. And do we think that this is going to look pretty similar to cosecant x?
Yeah.
Do the y values seem pretty much repeated of what they were in the other table?
Maybe that's the same.
Just even think of the difference between sine and cosine, right? They have the same shape. That just the key is what's the start, right? Do you get that? If we're dealing with cosine being the reciprocal of this, the start is different. So one thing you should notice is where are the asymptotes this time?
Pi over 2.
At pi over 2 and at
3 pi over 2.
so at odd pi over 2's. File that away for later. Odd pi over 2's. So 1 pi over 2. 3 pi over 2. Okay. So again, ignoring the root 2's, let's leave those alone. the numbers are still the 1, the 1.155, and the 2's, right? So it's the 1, a little bit higher than 1, 2, and then go ahead towards infinity, or -1, -1.55, -2, and then head towards negative infinity. It's the exact same pattern. You're still going to have these U shapes. It's just a matter of where the U's start. This time, where the first middle of a U starts right at the beginning, right? Because 0, 1 is a point on the graph. And then let's follow the pattern we just completed for the other one. 1 square over, 1.15 up, so slightly higher. 2 squares over, I'm at the pi over 3's, I'm at 2. And then off to infinity. So there would be that half. When I move to the next section, where should this U be? It should be all the values in the middle part here are all negative. So we're talking about one of the U's that opens down. Right in the middle, -1. One to the left, one to the right, a little bit less than -1. A little bit less than -1. I feel like I'm singing that song about show it a little bit lower. Okay, so a little bit lower, and then -2. And then once you have those 5 points, the shape should be it should be easy to do. And then if I end with the last little chunk, the end at 2 pi is at 1, 1 square over, 1.15 up, 2 squares over, 2 up. So I know it looks a little off, like it's cut off a bit, but you guys get that. Remember, you're only looking at a piece of the bigger picture. If I wanted to complete it, like I just complete this U, put a U, here's a U, and like you just keep doing that same pattern over and over and over again. So to complete your graph here, okay, 1.15 up, 2 up, and then -1, a little bit lower than -1, a little bit lower than -1, -2, -2, U. Okay, then 2 pi, 1. 1 square over 1.15. 2 squares over 2. Whee! Okay. So there's what cosecant. Okay? We'll fill in the info for this, and then I'll give you back your test, and we'll do cotan tomorrow to start the lesson. My goal tomorrow will be do that, talk briefly about inverse trig functions, and try to cover the word problems with trig.
Oh.
Then we'll be done the unit. That's it. Okay, so we're done the unit tomorrow. Just a big picture, done unit tomorrow. Wednesday's going to be a catch-up period. I'm not here, looking at AP applications, so you're working on just getting caught up and starting the review. Thursday, we'll talk about the test. I'll give you a test checklist. And then Monday after the long weekend, because Friday's a PD day. Okay?
Oh.
Friday's a PD day, so you'll have your test on the Monday after that weekend. Okay? That's the game plan. So let's fill in the chart. So let's start with the bottom thing. What's the general form for the vertical asymptote? This one's a little trickier. How would you describe the location of every vertical asymptote here? We used this analogy last week. Pi over 2, 3 pi over 2. The next one would be 5 pi over 2, 7 pi over 2, 1, 3, 5, 7. Odd. How did we represent odd?
2 pi plus 1.
Close.
3 pi plus 1.
Yeah, you got to rearrange some letters there. So x equals a number that always means odd times pi over 2. 2k plus 1 will always be odd, because k can be any integer, right? You times it by 2, now it's all even integers. You add 1, now it's all odd integers. So now all odd integers are represented by 2k plus 1. Okay? If that's where the asymptotes are, it's where the domain does not exist. So x element reals such that x cannot be 2k plus 1 pi over 2, where k is an integer. Range, same as for cosecant. All negative numbers less than or equal to -1, and all positive numbers greater than or equal to 1. Period of this function, How often does this pattern repeat?
Every 2 pi.
Every 2 pi. Okay, general location of local maxes. How would you describe these locations? Local maxes?
Every pi.
Well, careful, okay? If you say every pi, that means you're saying at 2 pi it's a max.
Every 2 pi.
Every 2 pi starting at a pi.
Yes.
Every odd pi.
Yes.
Pi, 3 pi, 5 pi, because you'd skip the even pies, right? If you did pi plus 2k pi, I would give it to you. But I know a shorter way of saying that is 2k plus 1 pi. And then where are all the local mins? At 2 pi, 0, negative 2 pi, 4 pi, 6 pi, 8 pi, 10 pi. So every,
2k.
you got it, every even pi. Excellent. Okay, so I'm going to stop the video. What I would recommend to do tonight, again, all of the homework from 6.1 to 6.4 should have been already done. Use this tonight as a catch-up day if you haven't go through all that. If you've done all that, you can fill out 5 out of 6 of this as your review sheet of summarizing all the rules. Okay? Thank you.